Howdy, our project is titled Miniature Autonomous Robots for Pipeline Inspection. This project is part of the Aggie Challenge program in the fall of 15 and carried out under the advising of Dr. James Boyd. The grand challenge addressed by this project is to restore and improve aging pipeline infrastructure. The long-term goals are to create a system which can reduce the costs associated with the transfer of natural resources and also to ensure safety of existing infrastructure, especially in urban environments. The technical challenges that must be addressed in this design are the miniaturization of the robot, the ability to harvest energy from the fluid flow, and mobility and navigation inside of a steel pipe. This is the end of semester robot design, consisting of a tracked robot chassis, energy harvesting system, and onboard electronics. The total robot size is approximately 4 inches wide by 6 inches in length by 4 inches tall, and weighs in at just over 1 pound. The energy harvesting system is based on a Pelton-style turbine, which has 14 conical buckets connected to a vernier wind turbine generator mounted on the top center of the robot. The body of the robot, which you see, houses the generator, the onboard circuitry, and the microcontroller, while also effectively decreasing the total drag on the robot and increasing the fluid flow to the turbine. The underside of the robot has a compartment which holds the LiPo battery used to power the robot and a permanent neodymium magnet which is used for adhesion to the surface of a steel pipe. The picture here shows the experimental setup used in the small air department wind tunnel. A number of experiments were performed using this setup, including testing the turbine geometry, which includes the shape and number of buckets, the height from the top of the body of the robot to the bottom of the turbine, and the effect of robot orientation on energy harvested. The plots seen here are the final results from the wind tunnel experiments showing power generated and efficiency of energy harvesting versus the airflow speed and the natural gas flow speed, the bottom and top axes respectively. The orientations shown in the legend correspond to the flow impinging on either the front, the side, or the back of the robot, respectively. The expected flow range inside of a live natural gas pipeline is approximately 6 to 20 meters per second, which corresponds to approximately 2 to 16 meters per second at the height of the turbine, depending on the pipe diameter. These results show that the robot can indeed harvest significant amounts of energy such that it may carry out an inspection task by making periodic stops to recharge the batteries. This video is a final demonstration of our robot, which shows our robot successfully moving in a steel pipe while harvesting energy from the fluid flow. Although not shown here, this test was performed with the robot upside down in the pipe, demonstrating that the magnet is sufficiently strong to cancel out the effects of gravity and drag.